Thank you, Abbas, Mr. Chairman. First of all, for organizing these sessions and inviting me. It's a pleasure to be here. I'm not sure if I know yet how to use the remote, but I'll begin by saying that I am a professor at UCLA. My areas of expertise are computational mechanics, structural earthquake engineering. But about a year ago, I started as a part-time consultant at Moffat Nichol, which is a company that has a worldwide footprint, and they work on many interesting projects that involve unusual structures. And when it came to modeling concrete structures using some state-of-the-art software systems, they were having some problems, some questions, and we have collectively embarked on developing some sort of an internal compendium within the company that could guide the Moffat Nichol engineers when they're trying to do designs or analyses of concrete structures, whether it's plain concrete, reinforced concrete, whether it is structures that lend themselves to idealizations of beams, plates, and shells or not, or whether the loading rates are slow, like in earthquakes, or really fast, like in explosions and implosions and impact. So this is going to be a long quest. We're just at the beginning of it. And so my title sounds very broad, but I will just focus on one subtopic in that realm. And that is the strain localization issues that people encounter when they do continue modeling of plain or reinforced concrete using concrete damaged plasticity models. This is one of the most widely used constitutive model for representing the behavior of plain concrete. And it has been basically proposed by Kachanov in the 50s and later perfected in mathematically, thermodynamically by people like Simo and Jew and others. And it found its way into many commercial codes, including LS-DYNA and Abacus. And my colleagues at Moffat Nichol have been using the version in Abacus. Because concrete is a strain softening material, this model suffers, together with the finite element method, from mesh dependency. And mesh dependency will manifest itself in different ways. You may suffer convergence problems in your equilibrium analyses. You may suffer bifurcations in your solution, or misestimate the load redistribution when some part of your concrete structure fails. This is because the basic concrete damage plasticity model lacks an internal length scale. When we test a concrete member in the lab or experience or observe its behavior in real life under an earthquake loading, for example, it behaves at a certain scale. That scale is the centimeter scale, perhaps the meter scale. And as far as the concrete damage plasticity model is concerned, it has an infinitesimal scale, and those do not necessarily match. So my goal in this area was to, first of all, understand what, for example, Abacus is doing to fix this issue and why it was giving my colleagues a hard time, and then see if we can actually remedy the situation by some other methodology. This is the problem I was talking about. If you have a strain softening material, physically, it may exhibit a behavior that you're seeing in this load deformation curve where some band of materials may fail, which will cause the nearby material to unload, and then the strain will localize, like in slope failures and things like that, and you can get it physically. And that may not be a problem. That might be the physics you're trying to capture. But if your numerical model gives you artificial softening, in that when you refine your mesh, you nominally expect your finite element method to give you a better result. But if your result is constantly changing, like you're seeing in the picture here, as you refine your mesh, your post-peak response is changing, then it's going to be a problem. Even if your objective is to capture the peak loads in a given structure, this is still a problem because your structure will not fail uniformly. Failure will be, again, localized somewhere. And if that failure is not correctly represented, other parts will get different loads than they would have. So even then, the overall load might be misrepresented. I wanted to kind of explain this to myself, why this is happening. So I created this little model problem that embodies the phenomenon here of a grain softening material. Imagine that I have two rods, one at the top and one at the bottom, connected in parallel. And I use a certain mesh for the bar in the top, let's say 5 finite elements. And then I put another bar in the bottom to maintain stability in my model problem, my thought experiment. Assume that all of the material that is involved in this model problem obey this constitutive law, where the internal force in any one of the bars is related to the relative displacement at the two ends of the bars through that softening relationship. And let's assume that the bar above has a softening relationship, but the bar below is always linear elastic. So it always can carry any kind of load you can apply to it. It has infinite capacity. So when you start loading this member, the load will be shared by the bar above and bar below. So the total load F of t will be just basic sum total of those two loads, whatever the internal load is in F6, plus whatever the internal loads are, and they should be uniform. If you cut a free body diagram, any one of those loads, whether if it's the internal force of member 1, 2, or 3, or 4, they'll give you the same. That should add up to F total. So let's, in our thought experiment, keep loading this. And let's assume that our internal displacement has reached a certain level in the members at the top, and then the internal displacement has reached another force level in the member at the bottom. So obviously the member at the bottom can just go indefinitely, but what will happen to our members at the top? If you work with any numerics, your finite element method is going to predict an internal force, and the return mapping algorithm that is responsible for enforcing this plasticity will give you an estimation of the force. And between those 5 elements, it's virtually guaranteed that those numbers will not be identical to each other. There'll be some noise, numerical noise. So let's assume that only one of those elements have reached, per accident, a tiny bit more than other elements in the link, the peak load. So what will happen next? What will happen next is that this element number 2, for example, the one I highlighted, will go over that peak threshold and reach the other side. But as soon as that reaches the other side, the other elements are going to unload. Yes, they are still going to have the same internal load. The loads are the same, but their deformations will be different. And once this happens, it is virtually impossible for members 1, 3, and 4, and 5 to reach over the hump and go to the other side. So they're going to keep unloading. So what is the overall effect of this? Let's just monitor what's happening to F of t versus the overall displacement that is experienced on the right-hand side. We're going to have a composite stiffness that you can see in the upper curve, and that composite stiffness will change when the first element yields. Let's say that's F2 in this case. And then it is going to be a reduced stiffness because now effectively the element 2 is contributing less to that stiffness. And it is going to continue on until element number 2 drops into the failure regime and completely break off, at which point all of the loads will be carried by the member in the bottom, F6. So the slope of that curve, the backbone curve, will converge to identically the stiffness of member 6. So now I guess you may be guessing why I put this member 6 in there, because I can subtract its force to get what's going on in the upper band to see what's happening there. But let's just ask ourselves this question. Members F1, 3, 4, and 5 are related to their relative internal displacements through this relationship. They all have the same material, same length. And then, of course, they're all bounded above by F ultimate. At this point, it's hopeless for them to ever climb back up to F ultimate anyway, but that is an upper bound for them. So this relationship tells us that as we reduce the size of the element, their stiffnesses are going to go up, and that is going to cause their relative displacements to go down. What that means is that they're going to become more rigidly moving relative to element number 2, and nearly all of the deformation that the upper chord experience will be coming from element number 2. So its stiffness is governing what's happening post-peak. So here's an illustration of what's happening when you use a finer mesh. If you use a finer mesh, initially the effective stiffness of the whole system is identical. and the ultimate will always be preserved, but the peak will shift to the left for every element. And what that's going to cause is that, again, the second element will kind of experience the most displacements, and it's the least stiff one. And this will manifest itself if I subtract that bottom curve from the top backbone curve. This is the effective forces that are being transmitted through the upper chord. And now you're seeing, as you refine the mesh, a softening response. So the response is not unique. As you refine the mesh, you're going to get a softer and softer peak, post-peak responses. And in this particular problem, this may not be an issue because you know the physics of this problem. It's easy to understand what's going on. You may not even need to do an analysis here. But imagine that this is a part of your structure in a huge structure, and this is a problematic corner of it. Now the load redistribution is all messed up. This is the problem. So Moffat-Nichol engineers were suffering from this, and they were, using whatever the remedy that was being provided in Abacus. And I'll get to that. The remedy that is provided in Abacus is number 2, viscoplastic regularization. I'll talk about that. And it is a patchwork of remedy. It's not like a physically consistent thing. It's just like, hey, let me just add some extra forces here to make it work type of deal. But there are other more consistent methods. In fact, there are energy-based methods that will take the fracture energy, fracture toughness from a test specimen and apply some regularization to your mesh, adjust your stiffness and damage parameters so you always get the proper response. There are more consistent plasticity models than the concrete damage plasticity model. These are non-local gradient models, which will sample your strains not at a Gauss point, but at a neighborhood of the Gauss point so that they have an embedded length scale in them. So this averaging will alleviate this mesh dependency, etc. So let's talk about the problematic model we have in Abacus, because other models are not necessarily available in Abacus. The one in Abacus is called concrete damaged plasticity. We call it CDPM, I guess. It is based on a basic Drucker-Prager yield surface. But unlike a Drucker-Prager yield surface, it also, unlike a plain Drucker-Prager plasticity model, it carries on an additional damage parameter, which evolves based on plastic strains and whatever is happening when you reach the yield surface and do loadings and unloadings. This damage parameter is D, and it simply scales the effective stress that was nominally representing the undamaged material properties, hence the name damaged plasticity. It's not damaged plasticity, it's damaged plasticity. There's a tiny nuance there, but once you see the equation, you clearly understand what they really meant by it. So this model gives you strain localization, and Abacus has created a viscoplastic fix for it. What Abacus does is that they take on the conventional plasticity parameters, damage plasticity parameters, and then they convert them into viscous versions. And my little analogy for that is the little link at the top is the one that is the basic damage plasticity model. The little box is like a slider that gives you plasticity. The spring is the elastic strain energy and all of that. What they do is they add a viscous dashpot, viscous term in there, which gives you additional force. So if you're having problems, this force is going to keep things intact. But how much of this force, how would you determine it? It's unclear. That's what's giving my colleagues a problem. Like, what should we set the value of this parameter mu that controls it? If you use too large of a mu, you're adding too much fictitious force and strength to your system. Not really strength, because if you waited long enough, presumably this will converge to that, but this is viscosity for you. And if you're using too little, you still have the mesh dependency. So once I've identified the roots of the problem, I kind of knew it anyway, but I had to dig through the literature. Then we realized that there is a group who came up with a good remedy for it, and that's Sergio Aller in Spain and his group, student Alfara. They wrote a fantastic paper that fixes this problem. So my contribution is really nothing except finding this paper and implementing it in a Python code, the algorithm for which is here, and I don't have time to go through that, but we can discuss it offline. And then, this fixes the problem. All it needs is your concrete strength, compressive strength that is obtained from a mesoscale conventional structural scale test. not a micro specimen, not a giant specimen of a dam, but like a regular sized concrete specimen. And then the mesh size you'd like to use with that strength. And then it automatically adjusts the rest of the parameters for Abacus so that it gives you a mesh independent response. Again, I'm going to kind of skip through the details, but we have done some verification and validation studies. The one on the left you're seeing is like a unit cube, which we apply uniaxial tension and shear and other things. And then we solve the same problem over and over again with different meshes with this technology and see if we get always the same result. If we do, this is really working. The one on the right-hand side is a more sophisticated, difficult problem. It's reinforced concrete, a portal beam, reinforced concrete frame. So there's a pushover test on that, and we try to capture those parameters. So this is just us verifying ourselves against our colleagues who wrote that 2017 paper to see if we've implemented their algorithm correctly. And then here's us applying it to this unit cube problem with different meshes. And as you can see, we have solved the mesh dependency problem. I'm not showing the negative results here, but the negative results without the fix will cause the post-peak response to soften indefinitely. More you refine, the softer it becomes. It almost collapses back onto the backbone curve. This is the pushover analysis. This is the calibration. Experimental measurements on the right-hand side. Our model analysis on the left-hand side for different mesh sizes, with and without the use of this regularization, consistent regularization scheme we got from Alpha-Ra. If we don't use it, it doesn't work. If we use it, it does work. Again, we've implemented into a Python Jupyter notebook that has a graphical user interface. You put your parameters, your mesh size, and it generates your Abacus CDPM input file, basically. You can copy paste it into your Abacus document. And also we've created a web version of it. So if you have the web address, you can go there. You don't have to download or compile a Python code or anything like that. And we're willing to share this with our colleagues. First and foremost, with our colleagues at Moffat Nickel, they're going to use it for different projects. But we want to share it with everyone who's interested in using the same kind of technology. So that's my presentation. Thank you.